Good morning, everyone. This is the walkthrough for the questions that are attached onto today's physics lesson. That's 12th of January 2021. You've got some questions. There are three past exam style questions, which you should have at least attempted by now. So if we are going through this, I did say on Show My Homework that I would start this at 10:30. There really isn't time for me to wait for very long, so which is why we're making a start now. I know not everyone's logged in. So question number one, an apple and a leaf fall from a tree in the same instant. Both apple and the leaf start at the same height above the ground, but the apple hits the ground first. We know that if air resistance was not a factor, they'd hit the ground at the same time because everything accelerates at 9.81 meters per second squared downwards when it's in free fall on Earth. Now, obviously, because they don't, this implies something very important. That's that air resistance must be coming into play. So it's obviously going to be part of the answer to these two questions. So it says you use Newton's laws of motion to explain why. We'll explain first of all why the leaf accelerates first and then reaches a terminal velocity. So if we think about it, the best way to think about it is you imagine you've got your leaf there. When it's initially being dropped, we know that the only force acting is mass times gravity because there's no air resistance yet because the speed of the leaf right at the beginning is 0. Okay. As the leaf continues to fall, we've got the same weight, but this time we have a force of friction. And as the speed increases, eventually the force of friction will increase such that it's equal and opposite to the leaf's weight. So that's what we're really looking for. So this is using Newton's first law of motion. So at the start, the speed is 0, so there's no air resistance. No air resistance, just the weight, and that implies acceleration. Now it says use Newton's the laws of motion, F equals ma, okay? So that's the idea, there's acceleration. We could say then, as the speed increases, then we know that there'll be more air resistance. More air resistance, which implies a lower net force, which implies a lower acceleration. Okay, then we want to say that eventually speed is such that the air resistance equals the weight of the leaf. Okay, so as the air resistance equals the weight of the leaf, that means the total force, the net force, equals 0. So there's no acceleration. And we call that final speed, a terminal velocity. Okay, so the idea is that the leaf initially starts to fall. As the leaf falls, it's moving downwards with a velocity. And that velocity is therefore going to give rise to an air resistance on the leaf, which is in the opposite direction to the weight of the leaf, which means that there's a lower net force, so the acceleration decreases, and eventually the force of friction of air resistance of the leaf is equal and opposite to the weight of the leaf, which means there's no net force. Now, this is the point at which people often say that the leaf stops falling. Of course, it doesn't stop falling. It just falls with a constant velocity called the terminal velocity. So why does the apple hit the ground first? Well, the apple is a larger mass. And because the apple's got a larger mass, it's less affected by air resistance. Because it's less affected by air resistance, it's going to have a higher terminal velocity. And that's the basic idea behind that terminal velocity question. So it's using Newton's laws of motion, but what we're basically saying is that we're looking at the sort of the net force caused by the weight and the air resistance. Now, a little caveat here. I've said here the apple is less affected by air resistance, which means it's less affected. Some people abbreviate this and say there's less air resistance. Well, that's not necessarily true. In fact, if the apple's falling quite quickly and has the same surface area as the leaf, then it would be then it would actually have a higher air resistance, but it's less affected because the air resistance is much less than the weight of the apple. So that was just sort of a preamble question, just to get you sort of started and get you thinking a little bit more detail about Newton's laws of motion. So we've got another question here. When you answer this question, you have to use your brain quite a bit here. So we've got a super tanker with a mass of 4 times 10 to the power of 8 kilograms. So it's a large number. It's got an initial speed of 4.5 meters per second, and it takes 1 hour to come to rest. So 1 hour is actually 60 seconds to a minute, 60 minutes to an hour. That's 3,600 seconds. And nothing wrong with annotating the question to make sure that you know that. So you want to calculate the deceleration. Well, the acceleration is going to be the change in speed over time. So rest would imply 0 meters per second. That's what being at rest means. So as a result of that, we can then say the acceleration is going to be the change in speed, which is 4.5 meters per second. Now, what's the deceleration? So it's a positive deceleration. If it said acceleration, we know this would be a negative number, but it's not. We divide it by 3,600 and we're expecting a very small number. So you plug it into your calculator. We end up with 1.25 times 10 to the power of minus 3. So 1.25 times 10 to the power of minus 3, and its acceleration, so it's meters per second squared. Now it's a deceleration, so it's positive because it's decelerating. If that's an acceleration, that number would have to be negative. That's all to remember there. So the distance traveled by the tanker while slowing to a stop, well, we've got to think about our SUVAT equations. We have given SUVAT. We want to work out the time. We know the acceleration. We know the change in velocity. We want to work out the distance, sorry. Okay. And we know the time. So there's lots of different ways of doing it. But what's probably easiest is to say, well, the distance traveled, S equals V minus U times T, sorry, V plus U times T over 2. Okay, that's the SUVAT equation that you can use. You can use any of them, really. You can, S equals UT plus a half AT squared. But I'm trying to avoid using that answer just in case I got that wrong. So, which I haven't, but just in case I did. So the SV plus U is going to be 4.5 over 2 multiplied by 3,600. We're expecting a large number. 4.5 divided by 2 multiplied by 3,600 gives you 8,100 meters. Well, I happen to know that it does take a tanker several kilometers to stop, so that's a reasonable value. It then says sketch using the axis below distance time graph. So what representing the motion of the tanker until it stops. And it's 2 marks. It wants some detail. Well, we're going to assume we start at 0. Now, if we think about it, the velocity is going to decrease. So we want the gradient to start off high and decrease, because the gradient of a distance time graph gives us the speed. So we have a gradient of a distance time graph, goes up, curves. Now at some point it's going to be stopped. So the point at which it stopped is about there. That's 3,600 seconds after travelling a distance of 8.1 kilometres, because that's what it was in the last question. Might as well put that on there because we've got 2 marks. It wants some detail. What it's really after, the main thing though, is this gradient ending up at 0. And so if it's not particularly clear here, I'm going to actually say gradient equals 0 at 3,600 seconds. Just to make it really clear that that's what I mean, because remember, when you're doing an exam, you're not being judged on your ability to draw or your ability to sort of sketch things in an artistic way. You're judged on your physics. So if you have put your knowledge of physics on something and it's not very, very clear from what you've drawn, labels are always helpful. It then says explain the shape of the graph you sketched in part B. So, well, first bit is to actually state the physics. The gradient equals the speed, okay? And we say speed decreases with time, so the gradient decreases. And we're just going to put that little flourish in there, that little extra sort of something else here. Decreases to 0 at 3,600 seconds. Okay, so you put that little flourish in there just to complete the question. So that's question 2. Now question 3, I think is quite a nice detailed one. Love applications. So most of physics is about its applications. So 1969 moon landing, the lunar module separated from the command module above the surface of the moon. It was when it was traveling at a horizontal speed of 2,040 meters per second squared, meters per second. There's a typo in there, that should be just 1s. In order to descend to the moon's surface, the lunar module needed to reduce its speed using the rocket. So it's a deceleration question. You're told the thrust of the rocket is 30 kilonewtons. That's 3 times 10 to the power of 4 newtons, always well worth annotating. And you've got the mass of the lunar module was 15,100 kilograms, okay? Calculate the horizontal deceleration. So we know that F equals ma, A equals F over m. This is easy. We know F is 3 times 10 to the power of 4 divided by 15,100. So 3 times 10 to the power of 4, so you press 3x 4, divided by 15, oops. We end up with 1.987 meters per second squared. Well, we've got a maximum really of 3 significant figures here, so we want to express our answer to 3 significant figures. So I'll say 1.99 meters per second squared. I hope that's okay. Then says, calculate the time for the lunar module to slow down to the required horizontal velocity of 150 meters per second. So you know the deceleration. So now acceleration is going to be delta V over t, which is V minus U over t. So it's a deceleration. So you want to work out the t equals V minus U over A. So I'm going to ignore the signs a little bit here because we just want to know a time. So the initial velocity was what was it, 2040, and the final velocity is 150. So it's 2040. 2040 minus 150 over 1.99. Well, I'm going to say 1.987. Okay, I'm just going to use a slightly more precise number. It's quite all right to use that one. That's absolutely fine. Remember, you're marked on your ability to show that you're on your understanding of physics, not on your ability to, not on what your calculator does, really. So 2040 minus 150. So you change the speed to 1,890 meters per second, divided by 1.987, tells you it takes 951.2 seconds. So would say my answer, well, I've got three significant figures, so it'd be 951 seconds.
Sorry, Gary, could you explain last question?
Sorry,
the acceleration.
I've got a lorry going outside. Can you say it again? Hello.
Could you explain the acceleration question?
This first one here. This one.
Yes.
Right. Thank you for asking. You're given the mass and you're given the force. And it's the force in kilonewtons, so it's thousands of newtons.
Okay.
So you've got force, you've got mass, you want to calculate the acceleration. Well, it says deceleration, so you know it's going to decelerate, so we're just not going to have a negative number. That's all that means. So we start off with Newton's second law. F equals ma. Force in newtons is mass in kilograms multiplied by acceleration in meters per second squared. So want to work out the acceleration, we just rearrange it. So if we rearrange that to make acceleration the subject, it's force over mass. Does that make sense?
Yes.
Does that make sense?
Yes.
Right. So once you know that, then you know the force is 30,000 newtons. So that's 3 times 10 to the power 4 divided by the mass, which is 15,100. Now they're not taking any into account the burning of the fuel here. Maybe that'll come later, but here they're just looking for the horizontal acceleration due to that mass. Okay, so that's all you do. That's all that is. I do apologise about the background noise outside, by the way. I don't know if you can hear it, but it's rather deafening. Nothing I can do about that. Anyway, so let's go back. Let's go back to this one. Back to these lovely questions. We're almost there. We're almost done. So we've got a rocket, which is then used to control the velocity of descent. Now, this is where we get a context question. You've got to read it carefully, make sure you understand it. Now, it tells you it's descending vertically with a constant velocity as shown. So it's constant velocity. So in other words, the thrust from the rocket is going to be equal to the weight of the module. So it says, due to the use of fuel during the previous deceleration, the mass of the unit module had fallen by 53%. Now you're given the acceleration due to gravity, and you have to draw force vectors in figure 2 to show the two forces acting. Now this is where you've got to be a little bit precise and just make sure you've got this right, because we've got 2 marks here. So it's not enough to say that you've got just one downward arrow, which is the weight of the lunar module, and the upwards arrow, which is the thrust. The arrows need to be labelled. So the label on here, well, it given you anything like that? No, it hasn't. You just got to label them. So this is the thrust, and this is the weight. Okay. Last bit, to get the second mark, these 2 arrows need to be equal in thickness and length, okay, to imply that they're equal and opposite forces. So that would be the last bit of that. Then you have to calculate the thrust force needed to maintain a constant vertical downwards velocity. So in other words, the force, the thrust, has got to be equal to the weight. So the weight is the mass times the gravitational field strength. Here, that's 1.61, okay? Common mistake the candidates made was they used 9.81 here because that's what it is on Earth. But actually, you've got to remember it's 1.61 because it's mentioned it in the question. And we know the mass is 53% of the original mass. So it's 0.53 multiplied by the original mass, which is 15100. So just calculate that. Oops, sorry. That gives you 8,003 kilograms. Obviously, that 3 is pretty irrelevant, but we're going to keep it in because we're going to use it for the calculation. So it's 8,003 multiplied by 1.61. Gives you 12,884.8. So 12,885 to the nearest Newton. How many significant figures have we got here? Well, all of our values are to 3 significant figures. So the value I'm going to quote is 1,200. So it's going to be up to there. Next one's above, next one's 5 or above. So it's 900 newtons. Okay. So that's the thrust force from the rocket. Okay. Then says when the lunar module was 1.2 meters from the lunar surface, the rocket was switched off. At this point, the velocity was 8 meters per second. Calculate the vertical velocity at which the lunar module reached the lunar surface. So we're looking for the vertical velocity. So when the lunar module was 1.2 meters from the surface, the rocket was switched off. So we've got a distance there. So at that point, it switched off, so it reached a constant velocity. So it told you the velocity at the beginning, this is u, is 8 meters per second. Calculate the velocity at which it reached it. So we know, we think about our Suvat equations. It's a Suvat question because it's accelerating constantly. We know the acceleration because we've given it earlier on in the question. We don't know the time, and it doesn't require us to calculate it, so that's not the right. So we don't need that one. We know we want to know the final velocity. We know the initial velocity was 0.8 meters per second, and we know the distance. So we're looking for a Suvat equation which has V, A, U, and S. So would this one be right? V squared equals U squared plus 2AS. We want to work out V. We've got U, we've got A, we've got S. That's going to work. So we substitute. Well, U squared is 0.8 squared plus 2 times 1.61 multiplied by the distance, which is 1.2 meters. So common mistake people make when they're doing this question as a real exam was they forgot to square 0.8. So I'm going to make sure I do that. 0.8 squared plus 2 times 1.61. That's the acceleration times 1.2. So then I press equals, and I get the answer of 4.504. Now, at this point, the other mistake in the examiner's comments, at this point, people submitted that as the answer. Why shouldn't I submit that as the answer? Why is that not the answer? Anyone? Any ideas? Why is that not the right answer? I've missed something. There's one step I haven't done. No? Okay, I'll show you. If that's the formula we use, that's calculating v squared, which is why it's really important to show that sort of thing in the working, because it reminds you. So you want to find out v, you've got to square root it. So it's the square root of 4.504. So you've got your answer here. You say square root, you press the answer button at the bottom here, and it gives you the answer. You press equals, that's 2.12 meters per second, okay? So 2.122 meters per second. So how many significant figures have we given here? Well, we've got 2 significant figures there, 2 there. So the answer is going to be to 2 significant figures. You can use 3 on this occasion, but actually that is your answer right there. Okay, 2.1 meters per second. I hope that's been useful to you. So what we did today was we covered Newton's laws of motion. We looked at the 3 laws of motion. We've looked at the basic meaning of them, what they mean. We did a little bit of historical looking at Sir Isaac Newton, because it's just interesting to know about. So that bit won't be in the exam, but the meanings of Newton's laws of motion. We also come up with a definition of the Newton, and we've had a go at some practice on some practice questions, and I'll be having a look at your Seneca work fairly shortly and feeding back. Where we're going next tomorrow, in tomorrow's lesson, we're going to start looking at momentum, the concept of momentum, and we'll use the concept of momentum to go back to the Newton's second law of motion, and we're going to adjust Newton's second law of motion to take into account momentum. I hope this lesson's been useful to you. Obviously, this is being recorded, so fairly shortly I'm going to be putting the recording up on showing my homework. It's available through YouTube. I also usually manage to put a link in for WeTransfer if you want to download it if you're in an area where you can't access YouTube. Some people prefer to use WeTransfer to download it. But otherwise, that is the basic nutshell of Newton's laws of motion, which we've managed to cover in just one day's lessons. Okay, any questions?
No, it's okay.
Okay. All right, well, I'll see you all tomorrow. Make sure you're logged in and make sure you're engaging with the momentum work tomorrow. So I'll see you all tomorrow morning. Have a good day.
See you. Thank you.
Thank you. See you.